Today we'll be discussing simplifying radicals, finding the intersections between intervals, and finding domains of functions. So jumping into our examples for simplifying radicals. This has come up a bunch in the homework, which is why we're now covering it. It's really helpful when you can actually think about what are all of our different squares. So if we think about 1 squared, 2 squared, 3 squared, 4 squared, and so on. We'll take it up to a few more values. And basically, we want to look for these squares to actually divide the given number under the radical anytime we're trying to simplify. So remember, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, and we could keep going. So you basically want to look for, do any of these numbers, 1, 4, 9, 16, 25, divide the number in our given problem. So looking at square root 50 x squared, first thing I'm going to do is break off the 50 with the square root of the x squared, and it's totally okay to distribute square roots across multiplication like this. We can only do it with multiplication. We can't do it with addition or subtraction. So now we handle these two separately. Like I said, with the 50, we're thinking about, do any of these squares divide the 50? Well, yes, the 25 divides 50. So then we're looking at the square root of 25 times 2, which that's what makes up 50, times the square root of x squared. Again, we'll handle the square root of x squared later. So now, again, we can break up our square root. This is really just showing all of my steps into square root 25, square root 2, square root x squared. Now, square root of 25, well, that's just 5. Square root of 2, we can't do anything with, so that's just going to stay like that. And then the square root of x squared, every time we have an exponent up here, I want you to, the easiest way to do it is to just divide that exponent by 2. So this is now x to the 2 divided by 2, which is really just x. We write it in the order typically 5 times x times the square root of 2. And that is the simplified form of 50x squared. So let's see another example. Now I have 72x cubed. So 72x cubed, let's break that into square root 72 times the square root of x cubed. Let's see, 9 goes into 72. 36 goes into 72. You can put that in a calculator if you have to see it. 36 times 2 is 72. So let's go there. So now I have square root 36 times square root 2. That was what made up the 72. Times the square root of x cubed. Now, the square root of 36 is 6 square root 2. And now we have x cubed over 2, which really is 6 root 2. And then we'll break up this x to the 3 halves as x to the 2 over 2 times x to the 1 over 2. Basically, I want to break off all of the even components I can out of that numerator in the exponent. And we might have an x to the 1/2 left over. Sometimes I like to think about it, okay, that's x to the 1.5, which means we have x to the 1 times x to the 1/2. Really, that gives us 6 root 2, x to the 1, we don't write the 1, and x to the 1/2, well, that's just square root x. So, putting this all together, we write the terms in grouped, basically grouping them like terms. So we have 6x square root 2x, all under 1 square root. We put them back under 1. So that's the long-winded way of simplifying the 72x cubed, essentially. Now to see the square root of 48. So we look at our list. Oh, 4 divides 48. What else do we have? 16 divides 48. It's usually easiest to grab the biggest one you can. Okay, so 16 divides 48. So then we have square root 48 times square root x to the 4. Okay, so this is the square root of 16 times the square root of 3, since 16 times 3 makes up 48, times square root of 4, x to the 4. And if we then go ahead and simplify this, I'm going to draw some lines so we don't get mixed up with the previous problem. So if we simplify this guy, now we have 4 square root 3, and then we do x to the 4 over 2, and 4 is even, so that makes that nice and simple. 4 square root 3 x squared. And we don't typically write the x at the very end. We write 4x squared square root of 3. And there's that one simplified. So now we'll see one more. And this time we actually have a 3 in the very front. But that 3 is just going to stay there for a while. We're going to ignore it. So let's see. 20 is divisible by 1 is divisible by 4. And I think that's the best we're going to get. So we're going to break 20. Let's break it off from the x first. And then we have 3 square root of 4 times square root of 5. Those two make up the 20. Square root of x to the 5. Well, that gives us 3 times 2 times root 5 times, now here's the other way to think about this x to the 5th. Sometimes it's easier to think, well, this is x to the 4th times x. So then we're looking at 3 times 2, which is 6, square root of 5, times, well, x to the 4th becomes x to the 4 over 2, which is just 2, and we're left with a square root x. So you don't necessarily have to break off that x to the 1/2 step. You can just break off one of the x's. Anytime that your exponent is odd, break off one of the x's and take the even part out and do your division by 2. Then we have 6 root 5 x squared root x, which again, if we write it in the normal order, we're looking at 6x squared root 5x. Put the things under the root together, just like that. So these take some practice to get used to them, but you'll see these pop up throughout the course. It's important to get that practice in now. Moving on to domains. Well, really, we deal with domains all the time because they're as intervals, right? And so today we'll be working on finding the domain of combined functions, which means that we actually have to find the intersection of two different intervals, two different domains. So we're going to practice doing that intersection step here, and you'll see how it applies during lecture. Typically, it's easiest to find that by just drawing out what your interval looks like on a number line first, and then seeing where they overlap. That's all the intersection means. It says, hey, where do these two sets, these two intervals, have numbers in common? So we'll start by drawing negative infinity to 1. To do that, I need a big open circle at 1. There we go. And we draw from negative infinity up to 1. Now I'm going to switch my pen color here so we can see the other one. See, this one goes from negative 2 included, so that's a closed circle, up to positive infinity. So positive infinity going that way. And so the intersection says, well, where do they overlap? Well, they overlap from negative 2 up until 1, right in here. That's where we have both lines. And so their intersection is given by, well, negative 2, and that's inclusive because we had a closed dot, up to 1. And that's not included because we had an open dot. But that's where the two lines intersect. That's where the two graphs on the number line kind of overlap, right? And so that's what we write down as the intersection. All right, we'll do that again. Going back to blue, I have negative infinity to 3 and 3 to positive infinity. So that's just a big open circle at 3 and covering everywhere else. And when we look at the second one, well, that says the entire number line. So we can all but not think about that one because there's no, it's the entire number line. There's nothing to necessarily worry about intersecting with. And so in this case, the intersection is just negative infinity to 3, union 3 to infinity, as it was in that first line. So moving on to the next one. We have negative infinity to negative 5 and negative 5 up to infinity. Means we have an open circle at negative 5, and we just keep going elsewhere. Now for the other one, if I go from negative infinity to 3, I have an open circle at 3, and it's covering everywhere else. So essentially my intersection says, well, let's not do everything, but we'll exclude the open circle at 5, keep going, exclude the open circle at 3, and then keep going. And so to join those two, we have negative infinity to negative 5. So basically we skip over negative 5. Oh, I need a union there. Negative 5 up to, well, then we stop again at 3. Union 3 to infinity. So we put the three pieces together, and now we found the intersection between those two intervals. Moving on to actually finding a domain algebraically. I wanted to get some practice in on this. It'll pop up today, so it'll be a good time to practice. And it is technically part of the 124 material, but like I said, especially with the first exam coming up, practice is always helpful. So, all right, when we're thinking about domains of functions, that is all possible input values, all possible x values. And the only two cases you really have to worry about are when you have a fractional function like we have in B, because we can't have zero denominators, or if you have a square root like we have in C, because we can't take the square root of a negative. Otherwise, in this course, for now, you don't need to worry about it. Those are the two things to think about when looking at domains. This first function doesn't have either of those cases going on, which means all x values are valid. So our domain is negative infinity to positive infinity, the entire number line. Now for part B, we do have a concern here because we can't have a zero denominator. No zero denominator. Which means we cannot have x minus 4 equal to 0. And that happens when x equals 4, right? I add 4 to both sides. So we have a 0 at x equals 4. So essentially my domain can include everything but x equals 4, which means negative infinity to 4 union 4 to positive infinity. Moving on to the next one. So here we have a square root. We have to make sure we're not taking the square root of a negative. It can be 0 though, because the square root of 0 is just 0. So we need x plus 3 greater than or equal to 0. If I subtract 3 from both sides, I get x is greater than or equal to negative 3. And so therefore our domain is all things above negative 3. So negative 2, negative 1, 0, 1, 2, up to infinity. Which means we'll start at negative 3. We'll go up to infinity. We'll use parentheses on the infinity like always. And because we have an or equals 2, that means I use a square bracket to include the negative 3. And that is our domain for this problem. All right, looking at part D, we have the square root of 2x minus 6. Here again, we need 2x minus 6 greater than or equal to 0. And if I add 6 to both sides, I need 2x greater than or equal to 6. Divide by 2 on both sides, and I need x greater than or equal to 3. So again, we're thinking, okay, I can start at 3. I'm going to go 4, 5, 6. I'll make this true. So we go from 3 all the way up to positive infinity. Parentheses around the infinity as always, and brackets around the 3, since we have an or equals to. And there's our domain for this function. So go ahead and give the rest of the worksheet some practice. The answer key is already posted. And please reach out if you have any questions.